So now let's take a look here. We want to talk about how to solve a related rate problem. A related rate problem is the kind of a problem we consider this as application of an implicit differentiation and the application of derivatives. So let's take a look here. How are we going to solve a problem like this? In any application problem, you have to read the problems very carefully. Make sure you understand what's going on there and what you want to find there. Okay, when we try to figure out the rate, you should immediately relate this to the derivative. Okay, in a calculus class, whenever you talk about some kind of rate, you have to relate this to the derivative. Okay, so this is a typical, very typical problems in the related rate problem. If you take a look at any calculus book, so this problem is going to be there. Okay, but it's not exactly same number or the same kind of story, but eventually going to be same thing there. So that's called moving ladder problem. So here we have a ladder 25 feet long, okay, be leaning against the wall of a house, and so the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So here, that's what we have here, and so that's the wall here. Okay, the base of the ladder pulled away, okay, is 2 feet per second. Okay, and so here now the first question asks us, how fast is the top of the ladder moving down the wall when its base is 7 feet from the wall? So which means when you pull this ladder, okay, away from the wall, and so that means this x, the distance between the base of the ladder and the base of the wall, and this distance keep increasing. Okay, x keep changing there. Okay, of course, when you keep pulling this top of the ladder gonna keep moving down. Okay, keep moving down. So that means the y distance is getting smaller. The x is getting bigger. Okay, x is getting bigger. So normally that's what we do in the calculus. When you x getting bigger, so the rate, we consider the rate change as positive rate. So that's reason, so here the 2 feet per second, we consider this as the rate of change of the distance x is equal to 2 feet per second. That's a positive. And so now when you pull this away, so the top of the ladder going down, the y getting smaller. So which means the rate of change for this, the y, okay, for this y, and that's because the y getting smaller, we consider that's got to be a negative. Okay, so for any problem, that's normally we consider this way. Okay, if you know that thing getting bigger, the rate of change, you're going to use a positive. Okay, if you know that's getting smaller, the rate of change, that's got to be negative. Okay, so now the question here is, when we pull this away, so that's moving down, so obviously this moving rate and this moving rate shouldn't be exactly same. Okay, it's not exactly same. So what we try to do here is how we're going to relate this two rate together. That's so-called related rate problem. In order to relate this two rates, so we first have to relate the x and the y. So pretty much, so here you can see this problem, if you don't look at the wall, the ladder, or anything here, that's pretty much you have here. This is x, this is y, This is the letter which is 25, which is a fixed length. That's 25, does not change. It doesn't matter how you move it. That's 25, always same there. So when you see this is a right triangle, when you see right triangle, how you relate all those sides together? Obviously, in order to relate those three sides together, we all know there is a theorem called Pythagorean theorem for relate the sides of right triangles together, which is this: x squared plus y squared equal to 25 squared. That's the Pythagorean theorem. So now what you do here is, because you know x dx dt, but you do not know the dy dt. We want to find the dy dt. So let's take a look here. Let's take a look how we're going to do this. Remember, when that's moving, both x, y depend on time. So that's the reason we consider x and y are functions of t. So which means both x and y depend on t. Okay. So that's the reason here, instead take derivative with respect to x. That's case, we take derivative with respect to t there. So here we have d dt x squared plus y squared, and 25, that's the constant derivative anyway, is 0. Okay. So x squared take derivative with respect to t. Not take derivative with respect to x. So now, when we take derivative with respect to t, we're going to use the so-called generalized power rule. X squared derivative is 2x. Because x depends on t, you take derivative with respect to t. So according to the generalized power rule, we have to find derivative of the x with respect to t there. Similarly, for this one, we have 2y and dy dt. Okay, the same reason like what we did earlier, okay, because dx dt is not equal to 1. It's not like you have dx dx that equal to 1, but dx dt is not 1. dy dt obviously is also not equal to 1 there. So now let's take a look, because we want to find the dy dt, because the top of a letter moving down, which is we want to find the dy dt. So let's solve dy dt. I have a 2y dy dt equal to negative 2x dx dt. I go ahead to use 2y to divide both sides. Dy dt equal to negative x divided by y dx dt. Okay, because I got a 2 reduced. Both got a 2 reduced 2. That's only got a y left. So now let's check here. Do we know x? Yes. When x equal to 7. Do we know dx dt? Yes, we do know that. That's 2. Do we know y? No, we don't know y. We don't know y, but we can find y. So because x, y, and satisfy this equation, so when x equal to 7, so you have 7 squared plus y squared equal to 25 squared. So all you need to solve y squared. Okay, so 25 squared, 625 minus 7 squared, which is 49. And subtract this here, which is 576. And the square root, which is 24. Okay, so now we got y equals 24. So finally, we put that in. We have a dy dt equal to negative x is 7, and y is 24, and dx dt, which is 2. So reduce 2 with 24, you get negative 7/12. That's feet per second. So you can see here, we initially when we talked about this, we said, oh, this dy dt should be negative because this negative does not mean it's not moving or something here. That's only means negative means moving downward because the distance of the y getting smaller. Okay, we use negative sign. Okay, so that's as we expect. This is negative there. So that's the answer to the first question here. Now the second is here, consider triangle formed by the side of the house, and ladder and the ground, so which is this, you have a triangle. We want to find the rate at which the area of a triangle is changing when the base of the ladder is 7 feet from the wall. Okay, so now we want to find area change because when you moving, so here, look here, if you ladder move to here, okay, so that means you got different triangle, and your ladder can move to and here. Okay, so you got all these different triangles, but it doesn't matter. You can see this is right triangle. When you have right triangle, its area always equal to the base times the height, which is x times y, divided by 2. So now I can write this area equal to 1/2 the base times the height. And also, everything depends on time t there, because when you're moving this, the x change according to the t, y change according to the t. Obviously, the area change according to the t, so we differentiate with respect to the t. The 1/2 you factor out, you only take derivative to the product of xy. And remember, this is product. It means you have to take derivative and use product rule. So you're going to have this dt and dx dt times y plus x dy dt. Okay, so now we actually know everything. Dx dt, which is 2, y is 24, plus x equal to 7. Okay, when 7 feet away from the base and the wall. And the dy dt, we just figured out. It's negative 7/12. Okay. So now all I need just figure out this number. So here I have 1/2 times this is 24 and minus and 7 times 7, because that's plus minus, that's why I'm changing to minus. So that is 49. 1/2 times 12. So here, I mean, 1/2 times 49/12, which is 24. Okay, 24. So all you need to just go ahead to find this here, 24, and okay, that means you got 24 square, which is 576 minus 49. Okay, so 576 minus 49, that's 527 divided by 24. That's the area change rate. That's a square feet per second. Okay, and so now we find the area of change rate. The last step here is find the rate at which the angle between the ladder and the wall of the house is changing. So you can see here, now I have this here. The ladder and the wall get an angle we call the theta. This is the y, this is x, that's 25. So here, I want the rate of a change, and when the x equal to 7. when the base of the ladder is 7 feet from the wall. So now, how are we going to relate this here? And we can relate the theta. Obviously, theta, we're going to relate the theta with x and y, okay, and the letters, and so on. So we can actually use many ways to relate this here. For example, you can use sine theta is x divided by 25, opposite divided by hypotenuse. Or you can use cosine theta, which is y divided by 25, whichever you want. Okay, so here, let's take a look. We just use, but we don't prefer use tangent, because tangent you're going to have x divided by y, opposite divided by adjacent. So then if you take derivative, you have to use quotient rule, which is related, you have to use both x and y there. But when we use sine, you only get one x there. So you don't have to use quotient rule. So here, let's take a look here. I have sine theta equals opposite, which is x, divided by hypotenuse 25. So now I differentiate with back to t. And remember that theta also depends on time t, because when it's moving down, you can see the theta getting smaller and the theta getting bigger. So here, when the moving down, you can see here the theta getting bigger. So that means we should expect the d theta dt is positive. We should, okay, because you can see the angle getting bigger. So let's take derivative. Sine theta, take derivative with respect to t. And this one, don't use quotient rule because 1/25 is coefficient. Then you just take derivative to the x, dx dt. Sine theta derivative, which is a cosine theta. And remember the theta depends on t, so you have to use the chain rule. The chain rule. You can't just say, oh, cosine theta. No, you have to use the chain rule. So here, d theta dt. So finally, so here I need to figure out what's d theta dt. So here, d theta dt equal to both sides divided by cosine theta. So I got 25 cosine theta and dx dt. So now, all I need just forgot everything here. I got 25 cosine theta. Cosine theta is adjacent divided by hypotenuse. When x equal to 7, we already know y is 24. So that tells us that, okay, the cosine theta is 24 divided by 25. Adjacent divided by hypotenuse, which you have 24 divided by 25. dx dt is 2. So I got 25 reduced, 24 and 2 reduced by 2, that's 12. So equal to 1/12. Okay, so remember, this is the reading per second. So we are done here. So finally we have the rate of change for the angle is 1/12 reading per second when the ladder is 7 feet away from the wall. Okay, so that's the end of this problem. How to solve a related rate problem. Any related rate problem, you have to make sure and how to set up initial equation. Most related rate problem in the calculus, okay, calculus 1, and actually relate to the geometry. Okay, relate to geometry. So that's reason you have to know the geometries, the formulas. Okay, triangle, rectangle. Okay, and all this kind of relate to the area. Okay, perimeter. Okay, all that's kind of formulas there. Okay, so that's the end of this video.